Hello, Professor Sargent here with you again. We are doing another flipped classroom lesson. This is for section 10.2, day 2, and it involves 3 examples of solving an exponential equation. An exponential equation would be an equation where the variable is in the exponent. And then we're going to see 3 more examples after that, which are involving arithmetic, plugging into exponential functions.
Y equals 4 to the x is a exponential function. It's 1 to 1. And 64 is a power of 4. It's 4 cubed. Because it's 1 to 1, the fact that we're getting equal outputs means that the inputs, x and 3, have to be equal. Y equals 10 to the x is a 1 to 1 function. We've got a million, or 10 to the 6th, on the right hand side. And because we're dealing with y equals 10 to the x as a 1 to 1 function, equal outputs must mean we can track back to equal inputs and x equals 6. You may notice that 64 is a power of 2. It's 2 to the 6th equals 64. So you might hope that 729 is a power of 3. In fact, it is. We could hope that 3 to the 6th equals 729. Let's check that. And yes, 3 to the 6th is equal to 729. You might wonder, what good does that do us? Well, we know that there's a rule for exponents that will allow us to either break up or put back together either multiplication or division when we have the same exponent. And so we can rewrite that right-hand side as 3/2 to the 6th power. And then you might still wonder, what good has that done us? Because we've got a base of 2/3 on the left, but 3/2 on the right. Well, one's the reciprocal of the other, and that's where negative exponents come in. So I'll rewrite 3/2 to the positive 6 as 2/3 to the negative 6. Y equals 2/3, all of that to the x, is a 1 to 1 function, and so equal outputs must track back to the same input. And we have that x equals -6. Doing a little check, dividing 729 by 64. We've got 11.3090625. Whereas if we raise 2/3 to the -6, make sure that's negative, same result as 11.390625. Exponential functions have a lot of applications to the growth of an investment in finance, to the growth of population in life sciences, and in chemistry, to the decay of radioactive elements. So here we are asked to find out how much was initially present at time equals 0 when we have the amount A of radioactive material in an ore sample following this exponential function. T is time in months. So we're going to multiply negative 0.5 times 0, raise 3.6 to that power, and multiply by 350. So 0.5 make that negative and multiply by 0. Of course, that's just 0. And then 3.6 to the power of 0 is just 1. Multiplying that by the 350, we've got 350. Notice that 350 was the constant multiple of the exponential part. Although 200 is the initial amount, we want to find out how much there is 6 months later. So negative 0.5 times 6, raise 3.5 to that power, and multiply by 200. Negative 0.5 times 6 is negative 3. We want to use 3.5 to the negative 3 power then. Make sure that you've got that exponent negative, and multiplying that by 200. We're supposed to round to the nearest hundredth, i.e. 2 places. So that 4 in the third place, we're going to round down to 4.66. Here we have an item at a business depreciating or decreasing in value according to this function. B is the value, T is the time in years. The original value, we're putting in T equals 0. Negative 0.25 times 0 is still 0. 2 to the 0 is 1. Multiply that by 8,000. So it started out with a value of 8,000. 5 years later, negative 0.25 times 5 is negative 1.25. It's 2 to the negative 1.25. Again, make sure that you've got the negative on that exponent. Different calculators may get there in different ways. Got to multiply that by 8,000. And we're supposed to round to the nearest dollar. So the 5 after the decimal point, that's going to round up to 33.64. $3,364. 10 years later, negative 0.25 times 10 will be negative 2.5. So I have to find out what 2 to the negative 2.5 is and multiply that by 8,000. So 2 to the negative 2.5. Again, make sure that you've got a negative exponent. Multiply that by 8,000. We're supposed to round to the nearest dollar again. That 2 after the decimal point is going to round this down to 1414. So $1,414. And the last part. All of these seem to show some exponential functions that are decreasing as time increases, but we want to make sure we have an initial value of 8,000. And this one, part A, is starting out at 10,000, as well as what we have in part D. So it seems to be down to, if we're going by thousands, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. Seems like it's going to be either part B or part C. If I zoom in on that a little bit, the choice in C appears to be 10 years, giving us about 1,000, whereas in part choice B, somewhere between 1,000 and 2,000. That seems to me to be closer to the 1414 that we found in the previous part of the question. So I'm going to choose B. That's all for now. I hope it's helped. If it has, please like the videos and subscribe to the channel. I'll see you again real soon.